We've been talking about collisions in one dimension. They are so much more interesting in two dimensions. Now, what I want to show you today is that just like solving a two-dimensional kinematics problem like projectile motion was as simple as solving two one-dimensional problems, a two-dimensional collision problem is just as easy as solving two, count them two, one-dimensional collision problems. I'm going to introduce this topic by taking us on a field trip. We go down to the hockey rink, and we've got these two hockey pucks on ice. And one's going north and one's going east. They're both regulation hockey pucks, with the exception that we've modified them a little bit, so that when they hit, they stick together and have a maximally elastic collision. So if I have these two hit and stick together, which direction are they going to go off at with your clicker, please? Now leave your clicker out. We're going to do about 5 of these. Okay. Good. C is the correct answer. Now, suppose I replace one of the hockey pucks with a Mondo hockey puck. But they're both going the same speed. And now, which direction is going to be most likely after they stick together? I was going to say it's not rocket science, but yeah it is. Okay. Good. B is the right answer. Thank you very much. Okay, this time I go back to the regulation hockey pucks. This one's going fast to the east, this one's going slow to the north, and they stick together. Which direction is most likely the result? Okay. The answer is D. Good. One more time. This time I have a Mondo hockey puck going slow. I have a regulation hockey puck going fast. And the question is, what direction, which vector best represents the final velocity? A can't tell, B is B, C is C, D is D. So last time. Okay, that looks like all of us. Okay, you said C. The answer is A. And here's why. What you were thinking is, oh, that one's got a lot of mass, but not so much velocity. So when I multiply the lots of mass with the little velocity, it'll wash out. Well, my department head, it turns out, is taller than me. If we take the number that represents our heights, he wins. However, it turns out that I'm heavier than he is. If we take the number representing our weight, I win. Height and multiply it by his weight, and we do the same thing for me. Are we going to get the same number? Not likely. Not likely. It's once in a blue moon you'll be lucky. Okay? So how do we solve these problems in two dimensions? We recognize that momentum conservation is a vector equation. That means it has to be true in the x direction and in the y direction. And when we conserve it in the x direction and the y direction, we get our answer. Now, before I go any further, I just want to point out that this is, like I said before, this is real physics. In 1995, a crazy person, Timothy McVeigh, blew up the Oklahoma City Federal Building. Now, authorities knew that it was a rental truck that had been parked, and then it had been filled with explosives and it blew up. Now, they just didn't know who put it there. Now, the way they solved that mystery was with that equation right there. They assumed that the truck was parked, that he wasn't driving past, he wanted to get out of there. And so that meant that the initial momentum of the bomb was zero. Zero. Zero in the X direction, zero in the Y direction. That means that after the explosion, no matter how messy, the momentum of that truck had to be zero for all parts of the truck. So they went and they gathered all the parts of the truck, and they found a part there, and they figured out how fast it had to be going to get there. They found a part there, and they figured out how fast it had to be going to get there. When they added up all the momentum of the truck after the explosion, it didn't add up to zero. There was momentum missing that direction. So they went that way, and they found a piece of the axle which had the serial number on it, which led them back to the company that rented the truck, which told them who rented it. And that's how they captured Timothy McVeigh. This is real physics that works in everyday life. And that's also the way rocket science works. Okay, so it's all on conservation of momentum.